I'm Raghu Krishnamurthy, so I'm one of the technical leaders in Datera. So I'm just going to do whiteboarding. Engineer, so I'll just do the whiteboarding of the architecture. So the way I'm kind of going to present the architecture of Datera is going through a product lifecycle of Datera storage platform itself. So let's talk about how does the Datera storage platform come into existence in terms of distributed systems so that it's ready for provisioning. And then we go take the next level, then how do we provision the Datera storage system for applications, intent, policies, and templates. And third, we'll also talk about how does this storage provisioning translate into storage deployment for access, basically. So it's kind of a three-step process, basically. So just to cover the breadth of the architecture, and then I can go deep in any of the architectural places, and then please interrupt me with questions so that we can have a good conversation around the whole thing. So when we started writing the Datera storage platform, there were 5 themes that we wanted to make sure that it is built up from ground up, basically. One of the things that we wanted to do was that let's do application-aware storage placement in our product, because we are building a scale-out storage at this point in time. So we need to make sure that we take application intent, what it wants to do from a service level objective, and appropriately place that data or even the access points, because we are distributed, so that it can give the SLO requirement for an application. So which means that we're always thinking in terms of application storage provisioning, not infrastructure or a volume level storage provisioning. In addition to application, we're also thinking about data services associated with the application. So let's make it implicit. Let's make it, let the application decide what kind of data services it needs, and then we can appropriately do the same in our storage platform. The second part of that is the intent-based provisioning that I talked about. That's one of the basic themes of the architecture. The second architecture is that there's no specialized hardware in our should be in our Datera storage platform, which means that we should be able to take a commodity hardware, and which not only has different kinds of media, different kinds of technologies built into the product, and eventually abstract it out in a distributed storage platform model. And that's where you can get the economic benefit of commodity hardware, commodity storage, and other stuff, basically. So that means that the main thing about economic benefit is more about heterogeneous node. As a distributed systems, we need to support heterogeneous nodes for technology refresh, for media refresh, or for memory and other refresh that happens in the system today, because commodity world goes really fast. Every 6 months there is a refresh of a hardware, and everybody's asking, okay, can you support in this hardware? We need to make sure that the platform is capable and agile of handling those requests, basically. The third part is that we are completely API driven and programmable at that point in the product, which means that it's an agile model. People can program to it. The storage will react to it, and then it will give the benefits that the application intends to have. So as an example, you saw in Bill's presentation, like suddenly you wanted to change the QoS requirements to 3K IOPS, and automatically all the instances that were running suddenly dropped down, basically. Which means that we want to make it completely API programmable. And the reason for that is when you have a cloud provider and a service provider, they want to dynamically change because of their cost structure that comes in during the time of the day, or a change that comes in over a period of time. You want to have that part of it, basically. The third part of it is that any distributed scale-out system needs to be multi-tenant, and multi-tenancy is a must in a distributed system. So we built our product to have multi-tenant, not only from like access perspective, like user access, user monitoring, not only from an RBAC perspective. We also built multi-tenancy from network segmentation perspective, storage perspective. So the whole awareness of the whole Datera storage platform perspective.
Are you doing any data encryption at the back end?
Right now, the current product does not have data encryption, and the upcoming release is where it's coming.
Would you encrypt by tenant in that case? So that each tenant had a data encrypted separately, so there was no risk of you?
Yes, that when I go to some of the policies and everything else, applies it by tenant, basically.
Okay, so you could apply that as well. Okay.
Then we also talk about network isolation and QoS, all in the context of a distributed platform, because the platform is just not about compute or storage. It also includes networking. It includes what it is connected to and all that stuff, which means that we want to make sure that though we may not be managing the switches or anything else because it's commodity, we want to make sure that we are aware of how it is connected, how it is, which ports are connected to which switches and all that stuff, so that we have an awareness to build and place data so that we don't have loss of data in case one node dies and things like that. So it's important for us to be infrastructure aware, basically. So that's the theme on which the product is based off, basically. So now I'm just going to start drawing the entire architecture as to how it's actually designed at this place. So the basis of our system is basically a set of commodity hardware consisting of storage, what we call as a storage node. And a storage node can be connected to in a variety of in a multitudes of ways based on how customers' networking infrastructure is. One way of connecting a system is that you can connect a set of storage system to a switch S1 and S2, and this could be on a completely different switches so that it is not only within a rack, the distributed storage node, it also can span across rack. So when people talk about scale out storage, it could be just within a rack and connect to the same set of switches for various reasons. In our system, we really don't care how it's connected to as long as we have a way to communicate to it, basically. And that's an important distinction. And this is where the data center awareness comes into the picture, is that we will keep track of how it's connected and so that we can allocate resources appropriately. So a storage node is...
So do you understand that the rack might be a failure domain and that sort of thing?
Yes, exactly. So if this is there's multiple failure domains in any distributed data system. So there are a few things which we can detect, which is a rack is a failure domain, so that we can place data across racks and all that stuff. But there are some things which we are totally unaware of, mainly from a power perspective. Whether even within a rack, some of them may be in one power domain, other one could be another power domain. Those are some things that are logically there.
Yeah, so one thing I wanted to add to that is that when we look at where Datera is placed, I talked about a 1,000 node deployment, that's about 100 racks in their data center. Typically for storage, physically, it's usually aggregated or in a separate section, its own row. Those things are protected fiefdom within data centers. With the Datera design, as Raghu is drawing, we envision being able to place storage within the racks as they deploy. So as you add more racks, there would be some number of storage nodes within those racks.
So is that to expose the endpoint physically closer to the application?
That is one aspect of it, because it gives us that ability to go from routed versus switch conversation.
Yep.
But it's also because when they buy the next rack, they really want to buy the same thing. They want it always to look the same, because their vendor, their VAR that's building these racks, I have database systems. One possibility is I go unique, database, web, and then a couple storage, or however they're going to do it. But the next one they plug in is going to be that same design. It just might have different components, because ultimately, the operators want to be able to buy from anybody and say, who's going to give me the best price for this 3 months chunk? The next rack could be an HP, a Dell rack, a Supermicro rack. That's what they want to get. Just want to add a little more context as to the multi-rack and why that failover piece matters so much. Is if I have 9 Datera nodes, 3 per rack, I'd want to spread them out for availability.
So each storage node, the requirement for our storage node is basically 2 things. One, it's completely high redundant, so we need a 10 gig network interface or a 1 gig network interface for accessing for the storage clients, which means that all the clients which need to access our storage uses a redundant network from a storage node. Then there is secondary network interfaces, which is a 40 gig interface by default, and that's mainly used for our backend network. So basically, we have 2 kinds of networking philosophies in our product. Basically, there is a access network which is used for client access. Then there's a backend network which is used for our distributed protocol, distributed data management, and things like that. Basically.
You said the access was 10 gig and the 40 gig is backend?
That is one SKU where we have backend is 40 gig and access is 10 gig.
Okay.
But it does not preclude both access and backend to be 10 gig. The reason for backend to be over provisioned is just to make sure that when you have a lot of nodes hitting an I/O, you have enough bandwidth on the back end to deliver that performance, basically. Okay. So it's more a performance metric, basically.
Okay.
So, and this is from a networking perspective. From a storage perspective, basically, we really don't dictate. At this point in time, we have multi-tier media in the storage. So each node basically has 2 tiers of storage in the current SKU that we are doing. So it has a disks, which is 12 of them. at 4 terabytes or 8 terabytes, so you get 96 or 48 terabytes. And at the end of the day, we also have a flash tier here at this point in time. So what we have done is that each storage node is capable of having multimedia within the system, basically, which means that we can do a capacity tier storage here, and we actually do a performance tier here. So it's basically used for a tiered storage protocol. But it does not preclude other nodes in the system to have different kinds of media. So which means that in another storage node is completely all flash, basically. And at the same time, another node, instead of having just one flash, it could have tiers of flash, that's MLC, TLC, or any of that. So it is up to the Datera storage node software to detect what kinds of tier it has and act appropriately for a capability or a serviceability of a storage node. And that allows us future technologies to come into the product without affecting other storage nodes. So tomorrow when 3DX points come into the picture, it could just be 3DX point and flash or disk at that point in time. So effectively, we can imbibe new technologies into each storage node because the platform is built for heterogeneous nodes. So this is just a storage node, and this is just a composition of a storage node, and all of them are connected to the same switch for access network and backend network. So what really happens in the whole product is that, now let's talk about how the whole how the whole system comes into play and becomes ready for storage services. So what Datera has built for a Datera storage platform is a Datera control plane. And what Datera control plane is basically a software that runs on every storage node. And on every storage node, we have a Datera control plane software modules that run. And the main purpose of this is to actually bring up all the storage nodes into a form factor that they're ready for storage services. And what it basically does is that here are the key points that the Datera control plane really performs. The first thing it performs is that it actually does a cluster membership management of all the storage nodes. So what happens is that when a system is being installed for the first time, one of the nodes is installed with all the initial configurations which is needed for call home support and backend IP addresses and access IP addresses. And from that time onwards, all other nodes do a networking broadcast or to get membership information. So basically they do self-discover themselves. And eventually the control plane that is running on the master starts accepting joining of nodes from all of the nodes basically. And cluster membership is based off standard raft algorithm. So we use HCD and we use raft algorithm for membership basically. So the other part of the Datera control plane on the master, what it does is that it also responsible for configuration management. What it means is that it stores all the configurations of the storage nodes as they come online. And it is responsible for doing configuration of the storage nodes. And in addition to configuration, it's also responsible for replicating the configuration to a set of other storage nodes. So one of the key things in the control plane that we have is that we don't have any control nodes at all. We don't have a notion of a control node which is doing membership and doing all that stuff. What we have done is that we have taken a subset of nodes and they form a control plane cluster membership, which means that what we call themselves is, it could be this way, it could be a set of nodes which form a cabal basically. What a cabal is a subset of storage nodes which are responsible for configuration management of the system basically. So those are the only ones that participate in membership. Rest of the nodes just join because they have an L2 broadcast and they can get to the node or get to the master at this point in time.
So it's the idea of having a cluster to avoid sort of split or partitioned configurations and so on. Is that what you're looking to do that for?
Yes. The reason why we are going to get a set of nodes is to make sure that when you have a split bin or a network goes down, you have enough membership built into the product.
And the decision to go across or down, is that automated? Is that
okay, this is where the the infrastructure awareness comes into the picture, is that each storage node, as it joins the node, it also gives enough information about its connectivity to the Datera control plane, and the control plane will start, it may start with if only this, if 5 of these nodes join the cluster to become members, basically, and then the rest of the 2 join later. We'll figure out that these 2 nodes are being part of a different failure domain. Then we'll evict 2 of these nodes and we'll make these 2 as membership.
You'll redefine
So
it.
exactly, the cabal is a fully running membership protocol, basically. So as nodes die, new nodes become part of the cabal. So it's never that we have only 6 set of control nodes. We actually have as many number of nodes that form the class that are part of the distributed system. So that's why we call it ourselves as we have a symmetrical control plane architecture. We don't have a separate control plane. And the reason why we need replication of configuration is because each storage node is completely shared nothing, which means that we don't share any data, so which means that every node that forms part of the cabal is being replicated. So once a storage node is asked to join, what really happens is that the storage nodes have control plane agents which starts describing its inventory and its profile to the master node, basically. So the first part of it is just the membership and the configuration part of it. The other part of it is basically a node management or a platform management. So every node starts describing what it has, how it is connected, what kind of storage it has, and what the capabilities of that storage, in which case we can actually profile the storage node as what it can deliver in the context of a bigger system. So when you have a bigger system, basically you need to know that, okay, this node is capable of doing 100,000 IOPS if it's an all-flash array. This node is capable of doing 30,000 IOPS because it's a mix of different capacity tier and performance tier. So all these things are abstracted out by the agent itself, and all we get is what it is capable of. So once the cluster is completely formed based on membership, configuration, and platform management, what you really have in the control plane is, okay, what resources I have, how are they connected, and what are the capabilities of each node in the system. And that gives us enough leverage about how to apply data provisioning philosophies into the cluster. And that's what we are looking at this point in time. When the cluster is formed, we know how it's connected, what it has, and how it needs to be used for provisioning techniques, basically. And that's the goal of the control plane from a platform management perspective. And in addition to this, we have the staple foot features of every storage product. We have audit logs, we have fault events monitoring, we have failure detection of all the components in the storage node. We have RBAC for user roles and user management. We have column support, which is a staple feature of every storage product.
And that's all API driven, right?
Everything is API driven. Everything in the product is API driven. It's a single management plane. So all you talk to is a Datera control plane, and you get access to all the distributed information from that plane.
But if I want to feed it to another monitoring tool or whatever, yes, I can do that also.
You could do that also, basically. In addition to that, we have had requests, even though we are a storage platform, we have had requests from customers that are using our product to enable basic SNMP read-only support, because they can attach their own monitoring tool like ObserveVM or something like that into our storage platform to understand what's happening. Yep. So, and we do provide support for basic monitoring tools on top of that, basically.
So Raghu, do you go back and remeasure or relook at that in configuration at any stage? Do you continually monitor?
Yes. So yes, one of the aspects of the control plane I was going to come back here is the other part of the control plane is the optimizer, basically. So the optimizer in the control plane is basically responsible for optimizing the way data has been placed and continuously evaluating the data that has been placed. And the reason for that is we have placed the data without knowing how the application is writing in terms of which chunks, where it's writing.
And you also might get some stupid network person
exactly.
plugs in something else into your switch infrastructure and screws up the latency or something like
exactly. that. Exactly. So the whole idea is the optimizer is the one which is getting feedback from every storage node with respect to its metrics, with respect to its behavior, and how much storage it's allocated. So what we do is that we feed that stuff, the optimizer stuff, into the optimizer engine, and then it'll reevaluate and tell that maybe it's better to move this storage from one node to another node. So that allows us to do continuous delivery of operation. This is not only true for our performance reasons, it's also true for our load balancing of the storage nodes. It's true for when you add a new node, we want to move storage from one to another. and it allows us to do that part of it, basically. So that's what the optimizer does. At the top of the things, we have a policy engine in the control plane, and policy engine is what is responsible for intent-based provisioning, and that's my next lecture where I'm going to talk about architecture of our policy engine, what are the elements of it, and how does it work, basically. And rest of the stuff is, of course, the control plane also provides UI and REST support at this point in time. So the way we've architected the platform is that even though we have CLI, REST, and UI, all of them are going through an intermediate process to talk to the Datera control plane. So it's very easy for us to add newer API technologies as they come in. We are not changing the entire infrastructure for API technology. What we are doing is that we are just changing the plumbing. So a UI request goes to an intermediate point where it's called the DCP interface engine. And all we do is we plug in a new infrastructure for that. And this is very powerful because we could actually do a PowerShell plugin and not worry about changing any of the infrastructure, because all we are doing is changing the interface at that point in time. And that's how we have developed our Python SDK for that matter. So our Python SDK, which we have, is actually based off our REST API, basically. So people can just use our Python SDK and not worry about REST and its object and everything else, because DevOps people like Python and REST nowadays both. So this is generally the architecture of the control plane from a platform management perspective. This is more to make sure that we have a right foundation for delivering application performance storage, basically. Any questions on this one?
So you haven't talked about how data is allocated across the system,
that's the
how
next,
it's protected, or things of that nature.
We haven't got there yet. I think you
So-
The data management, things.
so that's the next step is the provisioning and the production aspect of it.
Okay.
So this is I just want to set up a platform so that we have a platform which is there, good enough, so that we can do provisioning at this point in time. So we are now going to talk about how we are actually doing provisioning and how does the system provision storage for this thing. So when we looked at our platform and we said, okay, how do we want to provision, basically? And we said that in cloud and in orchestration engines, everybody is deploying storage in terms of applications. So let's look at what the application wants, basically, because we have a distributed heterogeneous scale-out storage, which means that we need to make sure that we can mix and match what the application intent is to the storage infrastructure we have. So that's where the Datera control plane comes into the picture from a provisioning perspective. So our unit of provisioning, when we look at all this stuff, instead of doing a volume level management and then, so if you take a traditional model of provisioning, which is also a model that has survived 20 years, so it's not that it's going away. So basically you always create a volume, V1 and V2 for an application, and then suddenly you realize that, okay, I need a snapshot service for all this stuff, but I need to take snapshots for both of them at the same time. Or what you do is that, you bring in another concept called a consistency group here in general, and then you allow snapshots to be taken at a consistency group level. So what we are doing is that we are trying to build a lot of things from bottoms up, from a volume and snapshot and backup perspective. So what we did is that, okay, let's take the same model, but instead of doing from bottoms up, let's try to do it from the top down, basically. And that's where an application intent provisioning comes into the picture. So what is application, or what does intent provisioning really mean, basically? So intent provisioning is a way of describing what your application wants and let the system dictate how it needs to pack the data, basically, how it needs to allocate the data, how it needs to allocate access. And that's exactly what we are trying to do here. And the basis of intent-based provisioning is scale up all storage provisioning to an application level. Don't do it at a volume level. Let's scale up at application level. Let people start thinking in terms of applications. What application do I need? What's the data life cycle of an application? What's the data services it needs? And that's what we want to do. And basically, the basis of intent-based provisioning at this point in time, the elements of it are application template, so application template is basically a manifest of what you want for your application. So it's a model view of an application, basically, how you want it in a very abstract way. And what it basically contains at this point in time is it contains policies for management for its application. What does policies really mean? It defines the rules of storage. So what do you want? Let's say, what's a QoS policy that you would want to have? That's what a performance policy would look like. A performance policy in an abstract way would look like, I want gold, I want silver, I want bronze. That's all it is. It does not tell what IOPS it has. The template itself does not tell you that. The definition of a policy somewhere else decides what the number is going to be. And I'll explain that in the next 2 minutes, basically. So that's what the policies is. We have a lot of policies in the system. We have policies for data redundancy, which means that how many replicas you want, whether you want like eraser coding and all other parts of it is data redundancy policies. We have policies for data protection, which means that how do you want to do snapshotting, what is your life cycle of a snapshot, all those things could be done as a policy. All of these are referenced by name. They're not referenced by values. They're referenced by name for a given reason, basically. And then you also have data placement policies. And why data placement policies make sense is that when you have applications like Hadoop and Cassandra, which runs on local storage and does replication by itself, when you translate that storage to our platform, we don't want to make sure that all the volumes are not allocated on the same node, basically. So if one node dies, then the whole storage goes away because it's a replica factor of 1. So what we want to do is that we want to build affinity rules in placement. So we want to say that, okay, I want you to create more storage, but make sure that they have anti-affinity into the system. That means that every volume is created on different storage nodes. So even if one storage node dies, it does not affect the application. So the idea is to take those intents and convert it into our product's behavior, basically.
So something like MySQL that might have multiple volumes, logs, and stuff like that.
Yes.
There's a template that describes the number of volumes that are required?
Yes, yes, exactly. So this is just the policies because they're referencing by name because what you want and all that stuff. Then the next part of the policies is actually the storage template, basically. This defines exactly what you want, basically. This defines what number of volumes you want, what kind of size you want, but it again will reference some policies. But the main attribute is how many volumes you want, what the size of the volumes are the main thing, because these are all concrete elements. These are not policy elements at that point in time. And you can also define all these policies, again, at a volume level. You can either define the policies at a template level, or you can define a policy at a storage volume level. The reason is that for normal users, you can define all the snapshot policies and access policies at an application level. And when you're talking about redundancy policy, do you really want 3-way replica for a redo log? Maybe 1 or maybe 3. So it depends on what you want. Or if you have a log volume in a MySQL, then what does it need, basically? So you can also define policies at the template level, basically. And at the end of the day, it also has something what we call as pools of storage. Pools of resources. And this is mainly a multi-tenancy and a micro-segmentation part of it. So when we have detected all our systems and everything else, we implicitly create pools of storage. But that's only from a physical connectivity point of view. But when you have a multi-tenancy and then you have a Pepsi and a Coke wanting to share the same storage, sometimes they want physical isolation, sometimes they want logical isolation, so it depends on what kind of isolation they want. So if they want pools of resources to be exclusively be assigned to them, then we can also create pools of storage. And so the resource pools are part of template. Again, they're referenced by name. It could say that, like, I am Coke Flash or Coke Pepsi or Coke Hybrid, whatever the pools of storage is. And this could be constructed manually, or it could be constructed by us based on failure domain. We always look at the connectivity principles and we'll allocate storage, but at the same time somebody wants a logical storage, we will do that. And the reason for that is...
Can one storage node have multiple pools of storage?
Yes. You can participate in multiple pools of storage, assuming that you only want within a multi-level tenant hierarchy, basically. So let's say that you have a root org, and then you have a Pepsi here, and then you have Pepsi HR, Pepsi ENG, or Pepsi this. Then these 3 things can share the same storage node pool, basically, can be part of different storage node pools. So it does not preclude us from doing a node belonging to multiple storage pools. So that's when you do that.
And are the storage pools, from a performance perspective, heterogeneous or homogeneous?
No, it could be both. It's left to the end user as to how they want to do it. By default, we would have pools for all flash, pools for storage and everything else. That will be our default pools. But once the policy says something else, we could have a storage pool which is mixed. And the reason for that, as we are doing the all-flash array, so this is one of the reasons why we are looking at it, is why does it make sense to pool both a heterogeneous node like a hybrid versus flash in the same storage node pool? And the way we looked at the system is that the way our system is designed, whether you have hybrid or all-flash, there is always a performance tier storage in the product. So which means that writes have the same performance whether you're on hybrid or an all-flash. So the only benefit that you get out of going to the all-flash, other than traditional SSDs and everything else, is the read performance, because you don't pay the penalty of reads. So what we decided is that, is there a way where we can have a pool of one all-flash array and two hybrid arrays, and you can create a three-way replica where one of them is on an all-flash array and two of them are on a hybrid array, because the write performance is not affected. The read performance, we can redirect the reads to only go to the all-flash array, in which case what you're doing is that you've suddenly reduced the utilization of the flash that you need, basically, because other two doesn't use all the flash, basically. So,
And as far as like RAID level protection, do you support RAID within a storage node?
no, the storage node itself today does not protect by RAID, but it does not today. And the way we protect by that is the replication factor today.
And you said 1 to 5 replication?
Yeah, 1 to 5 replication, yes.
And that's, when you say replication, you're talking within a cluster. Do you support like asynchronous or synchronous replication?
No,
between clusters?
that is coming in. Right now in the 1.1 product, no, basically. The 1.1 product, there's no DR replication. So what we do is that we do give access to the snapshot volumes and everything else, and we could use host-based replication for that purpose, basically. So we don't do asynchronous DR and all that stuff, basically.
So only synchronous in
Yeah.
1.1. Only synchronous.
Synchronous within the node, within the class.
Exactly.
So this is what an application template looks like. So what we are doing is that we have taken all this template and then we have defined pools of policies and storage. So one of the things that really happens is that just the definition.
So if I have one volume that I have a pool that spans 4 or 5 nodes, and I have a volume defined in that, does all the data for the volume go into one of those nodes, or is it?
No, it goes to all the nodes. I'm going to.
So it's widely striped. Okay.
Yes. So the next part is the translation of the template to a provisioning stuff.
Okay, good.
So we have the template. The template by itself is all names, references, and everything else. So what we do is that you instantiate a template, basically. And the process of instantiating a template creates an application instance. And what an application instance is, basically, is a concrete deployment view of the application template. And the way it works is that the application gets instantiated, the policy engine runs right now, and the policy engine is now going to figure out, okay, what does gold mean in the context of where it's getting applied? So an example of this template deployment would be, you can have one template for, let's say, MySQL with all the stuff, and you define template characteristics. And as you have, and then let's say you have 3 tenants, or dev, prod, and test. You can apply the same, and you can have different policies defined for each tenant. Basically, you can have gold is only 1,000 IOPS. Or let's say gold in production is 5,000 IOPS. Gold in test is only 300 IOPS, basically. So when you instantiate the template, and if you instantiate the template at this level, what it does is the policy engine will go and start resolving policies. Okay, which policy needs to be applied? So we figured, okay, you are in dev template and a policy has been redefined from a default policy to a new policy. So it will take G1000 as an IOPS requirement for that template. So when it hits in an application instance, it basically applies 1000 as an IOPS requirement for that application template. In order to answer Enrico's question that came up earlier, you take the same template and apply it to a test philosophy. Basically, we figure out that the policy is resolving to a 300 IOPS. So basically, you kind of get only 300 IOPS when it's instantiated in a tenant which has redefined the policies. So what that gives you is that you have a single template, and you have a second level of redirection for the policies, which allows you to be completely policy-driven multi-tenant, and you don't have to worry about, a common other way of doing it is that you can take a template, duplicate the template at all 3 places. It really works well. But then what happens if you want to add a new volume to a MySQL template? So what really happens is that now you need to go and change all the 3 templates if you want to do the same thing. So in our case, the concrete configurations of storage remains the same, and then the policies will resolve into an actual number for placement, basically. So till now, we just have talked about the policy engine finally translating into an application instance, which tells you, okay, I need to allocate storage. I need to allocate storage based on the optimizer. So this is where the optimizer comes into play and says, okay, I need a 3000 IOPS, and I need an all-flash array, and then a replication factor of 5. And that is where the data placement engine kicks in. So optimizer also does data placement in our case. So what the policy engine does is that it takes the template, converts it into an instance, and it also tells us that which storage nodes can participate in the data allocation scheme. And it's important because you have pools and resources which can constrain yourself, so you need to allocate to that particular stream. So once it is allocated, so what we do is that here is where a volume provisioning happens. So a volume in Datera's case is split into chunks, basically. And what we call basically is spans, or chunk spans is a common term that people use for a volume. And each span basically has redundancy characters that has been specified by the customer, which is if it's a replication factor of 3, there has to be a span of 3 nodes. So, and for each span, we go and figure out that which node should participate in the allocation of data for that one. So for these 3 nodes, it could be just N1, N2, N3, and if the storage node pool has N1 to N10. And this span could be N4, N5, N6.
So when you allocate that out, do you allocate?
This is still a logical allocation. It's a thin provision. It is just saying that this chunk of data from this volume should go to these 3 nodes.
Yeah.
And
But when you make that decision,
Yeah.
do you base it on the worst case or the best case? And I'll give you an example. So say you need 3,000 IOPS.
Yes.
You could look at it and go, I could do that on Flash.
Yeah.
And that Flash could be capable of doing 15,000 IOPS.
Yes.
But actually, if I did that, coming along in the future, I might have to move that because I might need something
No,
else.
we will take the approximate node which can satisfy that requirement,
okay.
not the best one. Otherwise, we'll be putting everything in Flash, and then we have to be migrating
And you'd
data,
have to be pushing
basically.
stuff down around all the time. Yeah, absolutely.
So for every span, what we do is that we will stripe across different set of storage nodes. And so what you get is a truly distributed allocation of data placement, basically. It could still be constrained by resources, pools, and everything else, but in eventuality, what you get is a span has a placement map, and a placement map has just a pointer to the storage node that will participate in I/O.
So
It's a little bit different than traditional stuff where people will use disk pools. We are not using disk pools in our product. We treat the whole storage node as a single blob of data. Servicer, basically.
So what happens if you have a request that you then can't meet the policy?
So when the policy requirements are not met and there is a force option to do a best effort at this point in time.
Okay.
So you do a best effort requirement, and then that should generally happen when you're running short of resources, and then the new resources can take 10-15 days to come up, like a new storage node or anything else. And then once a storage node comes up, the optimizer will rebalance the system to get back to the effort that you want.
Okay, but
so,
you wouldn't penalize anybody else who's already got an allocation.
No,
They would still keep everything they already had.
exactly.
So the allocation is static at first, and then the optimizer can actually take
Exactly.
place and move it around if you need to?
Exactly. So the reason we thought is that anyway we have to develop a system where it has to optimize continuously, because storage nodes are coming, storage nodes are failing. It's a commodity hardware, so it's going to fail more often than a specialized hardware. So which means that we continually have to move data. We anyway have to optimize that algorithm. So why not take the optimizer and first place data accordingly based on capabilities and services and everything else, and then as time goes by, as runtime I/O happens, that's where the metrics and the analytics come into the picture, and then we'll re-optimize it, basically. And of course, we also need to look at the cost of re-optimizing. There's always a fine balance between re-optimizing and all that stuff. But that's exactly what we are trying to do. Okay, so this is basically a span structure. So at this point in time, what it does is that it's just a volume layout allocation. It's not allocated no I/O or anything else. So in addition to the volume allocation, what it does is that the Datera control plane now spins up all the information that it needs for iSCSI. So which means that it needs to know what is its IQN. So we generate our own IQN at this point in time. So we don't have one IQN for the entire storage node. So we are a little bit different in that we generate an IQN for every application target that we do. Not only that, we also, as I said,
You create a target for everyone
For every
application gets its own target.
Yes.
So you then put a LUN. Each one of them
below
have
the
a LUN
target.
behind it.
Exactly.
Yeah, okay.
So we do a target, basically a target has an IQN. We also do a network portal. As I said, we also have pools of resources. One of the pools of resources is access IPs. So in our system, every application target can get its own IP address. Because we are using a pool of IP addresses, it can get an IP address. If you run out of IP addresses, we'll reuse one of the IP addresses and share the IP address. But what that allows us is that, number one, each application can have its own VLAN tag, so we bring in SDNism and IPsec for that application. If an application needs a secure IP channel, we could actually bring in IPsec into that channel. So because each application is completely independent, we could bring in a VLAN. Not only that, what it also happens is that in the future, the way we envision is that as SDN becomes more prominent, we want to make use of the SDN feature. So can we ask the infrastructure, network infrastructure, to do some bandwidth throttling for us, because we are VLAN based, we can be VXLAN based or whatever it is. So we can use the networking infrastructure to our advantage, basically. Because when you look at all this throttling, latencies, and QoS, once it hits the storage, it's all the storage that is doing the QoS. So, but the pushback can come also at different levels, and we want to see where can we push back it all the way till the end, basically.
So each iSCSI application
Yes.
has its own IQN?
Yes.
Is there a limit?
You don't like that, right?
I mean,
Is there a limit to it? Is there like
Those limits are, I
we
think,
can have 2,000 LUNs or?
yeah, we have systems which runs 4,000 LUNs basically, and at 2,000 targets basically. Because each target is, again, as I said, in addition to the span, we also decide which server will host the iSCSI target basically. So the iSCSI targets are kind of distributed all across the board basically. So which means that we can't have one iSCSI target, because if a node dies, we can't have a node-based iSCSI target, because the node has to get moved to another node. So we could move node from node perspective. I agree with that, because it's a management nightmare versus access nightmare. But other way around to look at it is, one of the designs of our system was, let's say a node dies and it was hosting 300 iSCSI targets. Now a traditional way that people do is that fails over, you move all the 300 targets to another storage node. So what happens is that the storage node now becomes twice busy, because every target is moved to the storage node. What we do in our system is that you get 100 targets die on the storage node, we can redistribute the 100 targets to the rest of the remaining nodes, because each one has an IP address. So it's a trade-off between how many IP addresses you want to use and how flexible you want to be. As I said, the access IP pools is constrained by what the administrator wants, basically. So if you want only 50 targets, and then we have multiple IQNs within the thing, we'll still go ahead and do it, basically.
so is it that appliance that actually manages all that?
Yes, the Datera control plane manages everything, so you actually don't manage anything in the system. Once you define policies, pools, and resources, it's all about end user doing storage provisioning, basically. So so you let the infrastructure admin define the resources he wants to do it for a tenant or anything else, and then you just use.
But then that manages all of those redirections.
Yes,
then.
exactly.
Okay,
So
all right.
the data control plane will manage node failures, will transfer iSCSI LUNs to iSCSI targets to another node, and since it's IP, we can redistribute across all the nodes. So you get a balanced system. So there's a trade-off between like management versus this thing.
And then snapshots are copy on write, copy on read, redirect?
No, snapshots are completely copy and write. So it is a very fast snapshot technique. You just take the snapshots and then you go with it, basically. So I was going to go, that's how it works. And it's at an application intent level.
So how much of this is open source and how much is your own?
All the control plane is our own. There's nothing that is open source there. The LIO obviously is open source target. The storage tiering layer, part of it is open source. There is a little bit of it which is in the user space, so which we don't do that part. The Datera distribution layer, which is responsible for writing IOs to all the spans and everything else, is it a Linux kernel module? So I'm assuming that it's an GPL, whatever it is, basically the standard kernel driver semantics. We have uploaded, I think, the Linux tarball as part of our product itself, whatever we have done at the Linux. We also enhanced quite a bit of things in the Linux platform in terms of LIO, in terms of C groups handling for QoS and everything else, which goes back to the community, basically.
Yeah, so the general answer is we do have, and this is where part of the really good performance comes from in the I/O, in the data plane. Everything that's in the kernel, which is generally single node generally, is obviously open source. Everything else on top, all the distributed parts, the control plane, the policy engine, a good part of the distributed data plane are closed source. They sit outside the kernel. That's the general policy.
Okay.
And the layer 3 adjacency, I mean, there was.
Yes, the layer 3 is coming in right now. For layer 3 segmentation or?
For the.
Oh, this is all layer 3.
Is there anything special
No.
regarding that? Is
no.
that just using?
It's standard using TCP/IP. There's
Okay.
nothing. There
All
is
right.
nothing. We have a way to use two kinds of transport, Ethernet-based transports. Today we use IP for all our distributed backend protocol.
Mm-hmm.
We could potentially use RDMA over Ethernet or RockU or whatever in the future when it comes over Ethernet.
Yep.
Then we would use it. The reason for that is that we are trying to make a scale-out stuff. Anything that you do with proprietary hardware, if it does not have subnet routing and all that stuff, you end up with all sorts of issues, basically.